All right, everybody. So today we're going to have a look at chromatography. So I've got another good start. There we go. So this video is going to be kind of separate to the spectroscopy ones in the sense that you don't really need to have a functional understanding of mass spec, IR, and NMR to be able to understand this, but it's going to go in that kind of overall field of Unit 4, Area Study 1, analytical techniques. So you also, it'll help if you have some kind of knowledge of chromatography before watching this, but I'll go over the concepts in a kind of basic way, just mostly a summary. Yeah, so it's probably better if you've already, we've already had the lessons and you've already read the textbook before you watch this. All right, so let's get into a couple of the core concepts here. So we've basically got three things that we can use chromatography for. It's an analytical technique, so we want to use it when we've got some sample. In this case of chromatography, it's normally a mixture, although you can use a pure sample potentially as well in a solution. But basically, we're going to have a sample and we want to find out something about it. So there's three different things we can do here. First one is that we can use it as a separation technique. So we can use it to physically split apart different parts of a mixture. Now, obviously, you wouldn't be doing this if you've literally just got one compound and it's in water and you know what it is. You don't really need to separate it at that point. But if for example, the classic is always a wine sample, or often it's just if you've made something synthetically, you've put some things together, you don't normally get 100% conversion of your reactants to your products. But you want to separate your reactants and your products out so you don't end up just carrying around your reactants everywhere and them having weird side reactions and stuff. If you want to get rid of everything that's not your particular sample, not your particular chemical that you want, you can use chromatography for that. And also allows us to separate samples, mixtures out so that we can analyze each individual component. This is particularly useful in terms of mass spectroscopy. They're often used in conjunction where you put something through chromatography and then you take the sample from chromatography and go analyze it via mass spec. If you have two different molecules in mass spec at the same time, it ends up being a bit of a mess. So you prefer to look at them one at a time. So second thing we can get from chromatography is that we can get some qualitative data. We can use retention times and compare those between different chemicals to kind of look at their polarity. And then lastly, we can find some quantitative data. So we can get a peak area whenever we run something through a chromatograph. And then we can compare those peak areas with known peak areas produced by solutions of known concentrations. And then that should give us, should tell us our concentrations. So in terms of what you need to know for year 12, you need to, from the curriculum, it says you need to know the principles of chromatography, which is a bit vague, but I'll explain it a bit more in a second, including use of HPLC. So it doesn't say that you need to understand TLC, paper chromatography, or gas chromatography. It does specify HPLC, and everything that I've ever seen in an exam question is HPLC. And construction and use of the calibration curve to determine the concentration of an organic compound in a solution. So again, the focus for this unit is on organic compounds, but it would be exactly the same if you're looking at anything else. I haven't yet to see an exam question on it, but it does specify here construction as well as the use of a calibration curve. So theoretically, maybe you could be asked to construct a calibration curve. I'll show you how to do that, but if you can make a linear graph, you should be able to do that anyway. So I've split that up here. So you need to be able to predict and explain differences in retention time. Retention time is going to be that qualitative data we were talking about before, and it relates closely to the principles of chromatography. So that's being able to explain it. Again, I've mostly seen explain questions on exams so far, but you should be able to predict things as well. And you should also be able to sketch and use a calibration curve to determine concentration of an analyte in a solution or in a sample. There we go. So let's have a look at the qualitative aspects of chromatography first and how it works. So separation in HPLC, which is the main type of chromatography we're going to be looking at, is going to be based on differences in polarity. So we're going to have Some compounds are more polar, some compounds are less polar, and they're going to be separated based on that. Now, as with everything to do with polarity, it's not that, even though we tend to say polar and non-polar, it's not that you have a completely polar molecule and you have a completely non-polar molecule and there's nothing in between. It's just purely based on a spectrum. So chromatography is able to separate all the things out on a spectrum. So you might have something really polar. You might have something really polar like methanol, and then you've got something less polar like octanol maybe. And then you've got something less polar like polar than that. Dodecanol, let's just go say for the sake of it. And then you've got something at the other end like hexane, which is completely non-polar. So it can separate all of those out as long as it's got enough time to do it. So we've got two options for HPLC, which is kind of logical. Basically, the stationary phase can either be polar or non-polar, and then the mobile phase has to be the opposite of that. If you had the stationary and mobile phase be the same polarity, you would get no separation. And basically, the bigger the difference with the polarity, the better the separation is going to be. So you either want a polar, stationary, and non-polar, or we want a non-polar stationary with a polar mobile phase. So basically, the idea here is that if you have an analyte, so something that we're analyzing, i.e. the chemical that we're actually looking at, if you're analyzing wine, then you're probably going to be using ethanol as your analyte because that's what you're trying to measure. That's what you're trying to look at. So if you have an analyte that's the same polarity as the stationary phase, it's going to adsorb, not absorb. Absorb is to go into it. Adsorb is to go onto the surface. It's going to stick to it more often than analytes of different polarities. So we normally think about this in terms of an equilibrium. So you've got your analyte, and I'll call this P for stationary phase. And basically, they can stick together and form AP, but they can also go back again. And basically, the higher the polarity, or the closer the polarity, I should say, the more it'll move to the right. And the bigger the difference between the polarity, the more it'll go to the left. So if you've got a polar stationary phase, if you have a polar analyte, it'll make lots and lots of these, and it'll spend most of its time stuck to the side rather than floating around in the mobile phase. If you've got something that's really non-polar, so you've got an alkane or something, it really won't stick to that. If you've got glass on the side, the non-polar hexane isn't really going to stick to the side there. So it's going to go spend most of its time in the mobile phase and just go along there. So there's different ratio of times, or basically the amount of time spent stuck to the side or adsorbed to the side is the better way to say that. The more time spent adsorbed to the side of the column is going to give us our separation. And it makes sense. The next step is pretty logical. If you spend more time being stuck to the side of the column where you're not moving, it's going to take you more time to come out the other end. So analytes that stick more are going to travel down the column more slowly, so they're going to take more time and therefore will have a higher retention time. So if you've got a polar stationary phase, the more polar your analyte is, the higher the retention time. Remember, it's retention time and not speed. So that even though your non-polar substance is going through really fast, it has a lower value because it's taking less time to come out the other end. It's how long it takes to come out the other end, we're not saying it goes out at 50 millimeters per minute or something like that. We just get a time value out at the end, and the closer the polarity between the analyte and the stationary phase, the longer it takes, the higher that retention time. So I've got a little animation here. So here we've got, so you should, if I just gave you this diagram, you should be able to predict, even if it didn't say what the column was, you should be able to predict what the polarity of the column is. So we see these red non-polar molecules are getting stuck to the side sometimes. So they're going along, and they stick, and then they come off, and they get stick, and they keep sticking, coming back off, sticking, coming back off. So they will get out the other end eventually. It's not like they get stuck and react and completely stay there. If that happens, then your chromatography experiment has failed, and you probably need to go buy a new column because you've got a bunch of chemicals stuck on the inside of it. At least with this type of chromatography. So for this one here, we can see that the polar ones aren't sticking to the side. The non-polar ones are. So the polar ones will have that lower retention time. Non-polar ones will have the higher retention time. And we'll end up seeing them coming out at different times, and we can go and analyze those ones separately if we want to. So that's the kind of qualitative aspect of chromatography. For the quantitative aspect, we've got our calibration curves. So when we actually look at a chromatogram, I should show you one. So they're basically going to look something like this, and it just has a bunch of peaks in it. You've got retention time on the x-axis, and you've kind of got arbitrary units on the y-axis, and you can measure that area under the curve. Now, the area under the curve doesn't mean anything by itself. It's going to be different between all the different devices that you're using. It's going to be different depending on your analyte. It's going to be different on, I don't know, the cycles of the moon or something like that. Basically, it's going to be different under different circumstances. So the only way we can get any useful information out of it is if we run two of the same analyte, two of the same compound or more in exactly the same circumstances and see what the differences are. Now, the advantage of this, or what makes it work, is that peak area scales linearly with concentration. So if you have a 5 gram per liter solution and you have a 10 gram per liter solution, the 10 one will show up with twice the peak area as the 5 one. So, but to do this, we're going to need several samples of known concentration, and they're going to need to be run in addition to the sample, and then we're basically just going to make a graph out of them. So this is just your typical linear graph stuff. We're going to do a line of best fit for it on the next slide. But basically, we're going to collect a bunch of data. We're going to run each of them. This is each a separate experiment. You don't all throw it in the same solution. You run your 0 grams per liter, you run your 2 grams per liter, 4 grams per liter, 6 grams per liter, 8 grams per liter, 10 grams per liter, and then you put them all on a graph, and then you run your sample and you say, well, where does that show up on the graph? So I said before that I show you how to make a calibration curve. So I've given you some data here, and basically with some different concentrations of some kind of chemical, and then the peak areas. So when we're doing a calibration curve, you're going to take your y-axis and make that peak area. If you've been given some kind of area unit like centimeter squared or something, you can put that in there. Otherwise, it's just going to be an arbitrary unit, so it doesn't really mean anything. And for the x-axis, we're going to put concentration. And we're going to have a unit here is milligrams per liter. So I'm going to put some little labels on this. Yes, I know it's ugly. All right, 100 there. And what are we doing? We've got 700 at the top. So let's go 700, 600. Obviously, you'd probably use a ruler for this and or use actual graph paper so it doesn't look like this. All right, there we go. So we've got some axes there. And then we basically take, these are our known solutions, so we're going to stick them all in there. So we have 20 is 100, 40 is 198, so it's around there. 80 is 405, it's about there, and 100 is 501. So it's, and then we do a line of best fit through it. So you can't actually take just 2 of those data points and find the gradient and the intercept and therefore know the linear graph. You can't use that to solve the equation. You have to use a line of best fit unless everything lines up exactly perfectly. So you can get the equation if you use Excel for this. But for this, I'm just going to have to draw my really dodgy line through the middle, and then we'll just base it off that line. So I've got 3 samples to show you a couple of different things here. So we've got 150 as our first peak area. So we can go across and we can go down here, and we can say that this one's probably about 30 milligrams per liter. Sample 2 is 300. So we go across, go back down, and it's probably about 50 milligrams per liter. So it's pretty logical. And then sample 3 is up here. And I'm going to come down here and say, okay, maybe that's 120 milligrams per liter. All right. So we can do a bunch of different samples at the same time. You can use one calibration curve for multiple pieces of data if you do it all under exactly the same conditions. And that is a kind of a time-saving measure because it's not as much fun to have to run 6 standards every time you want to measure a single unknown. You can just run a bunch of unknowns at the kind of the same day that you ran all your standards on. All right, so if we look at these three samples, we can start talking about whether whether our method is valid for determining those concentrations. So for this one here, it's pretty okay. It's between two data points. It's looking okay. For sample 2, we can see that the data falls between this big gap between the different points. So ideally, we want to have as many points on the calibration curve as possible, just so that if there's something weird going on in the middle, then you've actually got that on the graph. So this one here, we would actually describe as an interpolation. So, that'll work in a minute. Interpolation, which means kind of trying to predict stuff in between two data points that are pretty far apart. So we could technically say that this sample 2, the result might not be particularly valid, just in case it's not acting in a linear fashion in that area of the curve. And then if we look at the one that's at a peak area of 700, we can see that we actually had to extend the graph off the end. Now, you could say that that's about as bad as interpolation. It's a little bit worse though, just because often you end up with a graph that is linear to start off with and then kind of becomes non-linear. Well, it doesn't normally go down. Often starts and then kind of becomes non-linear as it goes further along. So you can see it's kind of linear for this area here and then stops being linear. And if our data doesn't actually go that far, then it's not actually good at telling us what the concentration would be out there. So I would say that this one here, this concentration here would not be a valid way of determining that. Now, how could we actually make that a valid way? Well, we could just add some extra standards in. So we could have another one at 120, we could have another one at 60, we could have another one at 140. If we added in the extra data points that were here and here and here, then we could pretty confidently say that those ones are there. But if we've got no data points there, if we're having to extrapolate or interpolate, then it's not going to be very valid. Now, you don't need to strictly know the name of interpolation or extrapolation, although they are nice words to use for data analysis. But just saying it's off the calibration curve or there's not enough points in the curve, normally the expected answers in VCAR questions. All right, so that's how we can plot and use our calibration curve. So we've got this far. The only other thing that really comes up with the calculations for chromatography is that you might have to backtrack a few dilutions. So that's kind of expected that you know how to do that. We'll go through a couple of them with the examples here, and they pop up a lot in the volumetric analysis as well. So make sure you can able to follow your logic through if things have been diluted. All right, so we've got one here at the start. Got some VCAR questions. We have a 12-gram sample of a vegetable is estimated to have a vitamin C concentration of 30 milligrams per 100 grams. The HPLC instrument used for the analysis produces a linear calibration curve for vitamin C concentrations between 0.02 and 0.1 milligrams per mil. Which of the following volumetric flasks made up to the mark will be appropriate for preparing the vegetable sample solution for analysis? So we've got a bunch of different ones here. We're actually going to have to try our different answers here to figure this out. So we've got this range of concentrations and we want it to fall somewhere in there. Because we don't have the exact value, we don't know what exact volume we're looking for. So we're going to have to try it at a few different ones. The first thing to do though is to use our first piece of data. So we have a 12-gram sample of a vegetable and we know that it's estimated that this is the case. So this is similar to when we were doing our titrations. We might estimate the we might estimate the volume that we need to add beforehand, just so that we know that we're kind of in the ballpark, even if we haven't done the analysis yet. So if we know that if we're saying that there's probably about 30 milligrams in 100 grams, and we have 12 grams, then we should be able to find out how many there would be in. If we know the concentration in 100, we should be able to figure out how many there are in 12, right? So 30 milligrams, and I'll multiply it by 12 divided by 100 because we've effectively got 12% of that over a 100, right? So I'll go ahead, multiply my 30 by 12, divide by 100, and I get 3.6 milligrams total. So we've got 3.6 milligrams. So basically, what do we need? What volume do we need to divide that by to get in this category? So all of these are just going to be a case of C equals M over V. Now we could do this the other way as well, and put the C in and the M in and find what V is. Actually, let's just do it that way. It's probably easier. So the volume is going to be equal to V. So the volume is going to be equal to the mass divided by the concentration. We know the mass is 3.6. The lower bound is 0.02. 3.6 divided by 0.02 is going to be, if I can successfully type it into my calculator, 180. Probably should have been able to do that in my head. So 180 mils here. And for our other one, we're going to have 3.6 for the upper bound on the concentration. 3.6 divided by 0.1 is going to be 36 mils. So our range is that we can use somewhere between 36 and 180 mils. 25 does not fall within this. 100 does fall within this. 250 and 500 don't fall within this. Therefore, B is the correct answer. Now, that's one way of doing it. The other way you could do it is, once you know your 3.6, we could just use the C equals M over V and say 3.6 and then test out all of these four values. 3.6 divided by 25 is equal to, it's going to be equal to 0.144. 0.144 is going to be above this concentration. So therefore, we can't use 25 mils here. And then you could try it for B, try it for C, try it for D, and you should find that B is the correct answer there for all of those, or the only correct answer out of any of those. So for our next one here, we've got some information here. Mobile phase used for a separation of two chemicals is either water or hexane. So you should, if you see water or hexane, you should immediately go, oh, water's polar, hexane's non-polar. If they're solvents, that's the main reason that we'd use either of them. So hexane is going to be a non-polar mobile phase. Water's going to be a polar mobile phase. And it says which of the following options gives the two chemicals expected to have the largest difference in retention time. So any two chemicals are probably going to have some difference in retention time, even if it's only a tiny amount based on whether it can stick to the wall or not. So if you have an isomer, maybe branched one is able to not stick to the wall as well, so it goes through faster. But they're pretty tiny. That's why it's saying which one is expected to have a difference, as it's saying which one is going to have the largest difference. So we would expect the one that has the largest difference is when we have one chemical that's polar and one that's very polar and one that's very non-polar. So if we have a look through them, the first one here, butanoic acid is quite polar. Carboxylic acids are quite polar there. Butane is an alkane, it's completely non-polar. So I'd say there's probably going to be a pretty good separation there. Next one, acetic acid is quite polar. Ethanol is quite polar. Carboxylic acid and alcohols are both polar. So we would expect no separation there, or we would expect some separation, but not a whole lot. Same here, ethanol, methanol, both polar. We would expect the methanol to spend more time stuck to a polar stationary phase than ethanol, but by a small margin. Butane, octane are both non-polar, so we would expect not a whole lot of separation there either. So A is going to be the correct answer here. All right, so here we've got a student doing an experiment. A student is designing an experiment to determine the concentration of aspartame in soft drinks using high HPLC. And then we've got three different things that can be in soft drinks. And we've got their retention times at different pHs. So this is something that you probably won't have come across, and the students this year wouldn't have come across because it's not something you need to know off the top of your head or anything like that. But basically, we've got a question here. According to the graph, which pH value would provide the largest separation? And this one here doesn't require, you don't need to know a whole lot of chemistry to actually be able to tell this one. We basically just want the pH value, i.e. the X value, that will give us the biggest gap between them. So our options are 3, 4, 4.3, and 4.5. 4.5 is obviously out of the question because we're getting no separation between the benzoic acid and caffeine. So that's pretty rubbish right there. 4.3, if I go 4.0, getting no separation between benzoic acid and aspartame. 4.3, we've got a little gap, and 3, we've got an even bigger gap. So we're just going to go with 3 because they're the furthest apart. Don't really need to know any chemistry to do that. Which one of the following would minimize sources of error and uncertainty in the student's experiment? Dilute the samples of soft drinks prior to analysis by HPLC. If the concentration was too high, so you were getting some weird effects, maybe, potentially, I'd put that one in the iffy category if everything else seems really dodgy. Use a different mobile phase for each type of soft drink investigated. Now that is a dodgy answer. Don't change your conditions in the middle of an experiment. Otherwise, everything's just going to be different. So B is obviously out. Analyze 3 aliquots of each sample of soft drink through the HPLC instrument. That looks pretty good. Writing anything in triplicate is just going to reduce your uncertainty. So I think that one looks pretty good. Increase the pH of the samples of soft drinks by adding hydrochloric acid. Adding hydrochloric acid is not necessarily a bad thing here in the sense that we get closer to this end, but the fact that it says that the pH will go up if you add hydrochloric acid doesn't make any sense, because if you added hydrochloric acid, the pH would go down because it's an acid. So D is obviously out of the question because the answer itself isn't internally consistent, doesn't make sense. So C is going to be the best one here. All right, here we've got a calibration curve already drawn up for you. We're measuring mass of caffeine in a particular coffee drink. So we've got a 5 ml aliquot of the coffee drink was diluted to 50 mils with deionized water. I'm going to just identify that straight away and say it's a 10-fold dilution. So whatever concentration we find at the end, the actual value in the original solution was 10 times that concentration. Make sure you pay attention to those, otherwise you're going to basically be off by pretty big factors. A sample of the diluted coffee drink was run through the HPLC column under identical conditions to those used to obtain the calibration curve. Well, that's good, because otherwise it would be really bad. The peak area obtained for this diluted sample was 2,400 arbitrary units. The HPLC column used has a non-polar stationary phase. The most suitable solvent for determining the concentration of caffeine in the sample is, all right, so we have a column that has a non-polar stationary phase. So that means we just want a polar mobile phase. Carbon tetrachloride is non-polar. Methanol is polar. That's looking pretty good. Octanol is kind of in the middle. Hexane is non-polar, so that one's definitely out. Methanol is more polar than octanol, so it's going to be the better solvent here. The mass of caffeine in grams in 350 mils of the undiluted coffee drink is closest to. Oh, let's go back here. So the original sample is 2,400 arbitrary units, so it's about here. I'm going to draw a line across, a super straight line across over to here, and our concentration is going to be about 0.04 grams per liter. There we go. And so if you go to the next slide, oh, they haven't done a trick question for that one. So that's the concentration of the diluted one. Now there was a 10-fold dilution, as I pointed out before. So the original, so the OG was going to be 0.04 times 10, which is going to be 0.4 grams per liter. So we'll go in here and we'll circle 0.4 and we'll get the answer wrong because we didn't read the whole question. So that is indeed the concentration of the original coffee drink. But it says the mass of caffeine in grams in 350 mils of the undiluted coffee drink. So we just need to plug this into C equals M over V. So our concentration is 0.4, our mass is 0.35. Remember, we're going to do this in liters. So M is equal to 0.4 times 0.35, which is roughly a third of 0.4, which is roughly going to be 0.14. There we go. So if you forgot to do the dilution, you'd get A and it would be wrong. If you forgot to be finding the mass, you'd get D, you get it wrong. All right, here's another one. HPLC was used to determine the sucrose concentration from a can of soft drink. And we've got some standard solutions. A 1 ml sample of each standard solution was injected into the HPLC column, yada, yada, yada. Experimental results. And here's our calibration curve, basically. All right, so we can see this is a pretty dodgy calibration curve. I would not be happy with this at all. But let's just say that that's not a thing. A 5 ml sample of soft drink was diluted to 100 mils in a volumetric flask. When I see questions like this, which are going to have a bunch of steps to them, I often like to, sometimes I like to draw a diagram to show what's going on. So we've got our drink here, and I'm moving out 5 mils into a volumetric flask, and then that's being filled up to 100 mils. You could also just say you could also just write down what is the dilution. So 5 mils into 100, 5 goes into 100 20 times, so it's a 20-fold dilution. I'm just going to go with my drawing here though. So I've diluted 5 mils to 100, and then from there I've moved 10 mils across to, what does it say, 250 mil volumetric. 250 mil volumetric there, and filled up to the calibration mark. So we've diluted it, and then we've diluted it again. So once we find the final one, we're going to have to go back to the starting one. You find that that's how it often works with these analyses. You've taken the original diluted, you analyze the diluted one, and then you have to find that concentration, undilute in the calculations to get back to that original one. All right, so let's actually get to the question. We have an area of 1900 millimeters squared. Determine the sucrose content of the sample tested in the HPLC in grams per liter. So the sample tested in the HPLC, not the original. So we don't need to worry about the dilutions here. I'm gonna draw a line across here. Often they like to put them at the junction between two lines just so it's a bit easier to read, which is very nice of them. So 0.3 grams per liter, and we'll go across and say, that was a nice easy mark. There you go. Calculate the percentage mass per volume of sucrose in the 5 ml sample of soft drink. So 0.3 grams per liter was the original one here. Now, when we're doing the dilution calculations, we're going to have to go back 2 steps to find the original one. So we've gone 10 to 250. Now you can say that that's a 25-fold dilution, therefore I'll multiply the concentration by 25. If you remember it from last year and prefer to do that, you can also use the C1V1 equals C2V2 equation, plug everything in there, and you'll get the same thing. So here would be, we don't know this one, we'd say V1 was 10 times C1 equals 0.3 times 250. It's the same calculation really. It's just whether you like doing the dilution factors in your head or not. Yeah, there we go. So we're going to do 0.3 times 250, which is going to get us 75 grams per liter in the original one. Is that grams per liter there? Yep. And then, so this was a 20-fold dilution. So I'm going to multiply that. Again, you can use C2V2, C1V1 equals C2V2. 75 times 20 is going to get a heck of a lot of sugar. All right. Just double check everything there. Going across 1900 millimeters squared, it's 0.3, 0.3 times 25. 0.3 times 25. There you go. It was supposed to be 75. I thought that was it. See how even though I made a mistake there, I think I forgot to add the decimal on the calculator. The fact that I've evaluated it in terms of what's actually a logical value to have in the soft drink, I've been able to fix myself up. So this should have been 7.5 grams per liter. And then therefore this one is 150 grams per liter. Still a lot of sugar, but it's not, it's not basically a saturated sugar solution. All right, so we've got 150 grams per liter. And we need to find so that would probably get you 1 mark here. Calculate the percentage mass per volume in the 5.0 ml sample of soft drink. Now, the fact that it's 5.0 ml doesn't really matter. It just means that it's the original one. We don't need to use the 5.0 in this calculation. So we've got 150 there, grams in 1 liter. So if we're doing percent mass per volume, we can do the mass that would be in 100 mils. We can also just say the mass divided by the amount of mils. So here, I'll show you both ways. 150 grams per liter is 150 grams divided by 1000 mils times 100 is basically just 150 divided by 10, which is 15%. Alternatively, you can just say it's going to be 15 grams in 100 mils. So therefore, it's going to be 15%. And I'll leave it at 15, just 15 there with the significant figures. All right. Can used to obtain the sample contained 330 mils of soft drink. Assuming that the only sugar in the soft drink is sucrose, calculate the mass of sucrose in the can of soft drink. All right. So I'm not quite sure why we have to assume that the only sugar is sucrose, given that we're finding the mass of sucrose. But anyway, so it was 150 grams per liter. So we had this here, 150 grams per liter. C equals M over V. We've got 330 mils, which is 0.33. i.e. basically a third. So M is going to be equal to 150 times 0.33. And then that should be basically just 50. 49.5, if we want to be precise. I had that to 2 significant figures, so I'm going to round that to 50. And our unit is grams. 50 grams there. All right. Based on the results obtained, is the experimental method valid? Give your reasoning. I really don't like this question. It's much easier to describe why something's invalid than to describe why it is valid. In terms of things that we could talk about here, we could say that it's used at the same conditions, so therefore it's valid. We could also make a point that the points on the calibration curve, like I pointed out before, aren't particularly linear, so therefore the result is likely to be inaccurate or have a significant degree of error in it. Something about those two would probably make sense. I'm just going to show you what VCAR said here. So only 10% of students actually got this mark here. So they said it's valid as the data is consistent for standard solutions of different concentrations made up from pure sucrose. I'm going to be honest, I don't know what that means. I think it's saying that the graph it's made is roughly linear, which from an analytical perspective, I think it's actually pretty rubbish. But if they accepted it, then they accepted it. Conditions used in HPLC were consistent across all the standards and the soft drink solution. As I said, they do say here that the sample solution, the peak areas were measured under the same conditions. So they did that, I guess. The peak areas for the standard solutions of the diluted soft drink sample were recorded at the same retention time. Again, I suppose they're saying because they say it's here, it's the same thing. It's just they said things are the same, so therefore it's valid. Or you could say that the method is invalid because there weren't enough points. Again, I think these answers are pretty dodgy. You could say that maybe a 0.3 and a 0.5 and a 0.7 would be nice to have in there. I probably wouldn't go and say it's invalid because of that. But again, I think it's pretty hard to argue. It's pretty hard to argue in one mark why something's valid. You would have to go through like 5 different reasons why the thing wasn't invalid. So I don't like this question. I feel like these answers are basically a couple of things that they've come up with for a question that doesn't really have a particularly good answer. But basically, in terms of if you are asked to prove validity, it would go with, I'll go with something about the curve being straight or not straight, and basically whether the conditions are the same or not. It's much easier. It's much easier to prove something invalid than valid, because if one thing is invalid, the whole experiment is invalid. But for something to be valid, basically everything has to be valid. All right. Yep, so as it says here, make sure you're actually saying something. It is valid because the result was obtained doesn't mean anything. You can get a very wrong result and it still be, you can get a result, you can get many results and still have them be invalid results. All right, and I think this is our last one. Researchers have developed a technique that allows HPLC to simultaneously determine the concentration of sugar, organic acids, and alcohols in fermentation products and food samples. Here's some retention times. What a cool technique. So we've got our chromatogram here, and we've got 4 different peaks here. Now, I'd be questioning exactly how well this technique is going to work if the peaks are overlapping, but again, another issue. Identify the substances responsible for each of the peaks Q and R. So Q is at about 15. R is at about, what's like 18 or 19, maybe. So Q is probably galactose, and R here is, if we say 20 is about there, could probably argue about which one it is, to be honest. I think it's probably, well, 18's there, so this one's probably closer to glycerol. R is probably glycerol. And the other one is galactose, Q is galactose. It'd be nicer if they had some succinic acid in there as well to try and distinguish between them, or at least some better access labels. All right, 2 substances have different retention times under identical conditions using the same HPLC equipment. Explain this difference in retention times. This is basically just explain the principles of chromatography. So we've got 3 hallmarks to answer this question. So again, we probably want to make 3 points. So I'll say something like different analytes, or you could say different substances. Different substances have different polarities. Substances adsorb onto the stationary phase. A different amount, depending on polarity. And therefore, substances that absorb more take longer to travel through the column, running out of space, therefore have longer or higher retention times. So basically something about imagining, you could also just have an example one here if you wanted to talk about ethanol and dodecanol and compare them there. Basically, we're only getting that separation because the substances have the different polarities. We're only getting the separation because they have different attractions to the stationary phase based on those polarities. So the more we could even add a 4th point in here saying, basically being really clear, saying the more they match the polarity of the stationary phase, the more they'll absorb onto there. So whichever one is closer in polarity to the stationary phase, the more time it'll spend absorbed onto there. And basically, the more time they're absorbed, the longer they're going to take. So basically, therefore, the closer the polarity of the substance to the polarity of the stationary phase, the higher the retention time, and vice versa for having dissimilar polarity to the stationary phase. And that's basically our 3 marks there. And that's most of the questions on chromatography. So again, it's basically those 2 kind of ideas. You can see a lot of the questions here aren't particularly complicated. So this one is basically just explain chromatography. This one is match the numbers onto here. The only reason this one's a little bit challenging is because I would say that R isn't very well centered over 20. But again, you could probably give this to someone who didn't know chromatography and they would get it. This one here was a bit wonky for the bottom one. The top one, you just needed to use your equation. Here we just needed to read it off the graph and then make sure that we do all the dilutions correctly. And then we know how to calculate percent mass per volume. Keep going back. We need to know that our stationary and our mobile phase should be as far apart in polarity as possible. And again, how to read data off the curve and then perform calculations with that. Again, this one was kind of common sense in terms of we like to get as many samples as possible run to get the best, to get the highest precision we can. So remember, we get high precision, not accuracy, from running the sample a lot of times. And we can also see that here with we can basically just read this graph, and it's more of a logic problem as opposed to specifically a chromatography problem. And then here again, we had a kind of more maths-based one. And then this one here, basically just knowing the principles. So if you're able to, if you know how chromatography works, you know how retention times work, and you know how calibration curves write, those are the 3 things that you need to know for chromatography. If you've got those, you should be able to handle anything that Vika or me in the SAC is going to throw at you. All right. Well, thank you for watching. Let me know if you have any questions. See you later.